Today we're going to continue talking about functions, and this is chapter 1.1 in your PreCalc textbook. Well, a function, as you remember from Algebra 1 and Algebra 2, it's a rule that maps an x. Usually we call it x. It's not always x, but usually it is. That maps x in the domain, and that x value is called the independent variable. That's an important vocabulary word, independent variable. To the y value in the range, and the y value is the dependent variable. Y depends on x. Whatever x is, y will be some kind of a function of it. For example, you've seen these kind of functions 100 times before. Let's say f of x is equal to 3x minus 4. It's just a straight linear function. If you want to evaluate that function at, let's say, x is equal to 1/3, you just substitute any x you see with a 1/3. So this is 3 times 1/3 minus 4. And 3 times 1/3 is 1, and 1 minus 4 is -1. So f of 1/3 would be, I'm sorry, -3. 1 minus 4 would be -3. The next thing, let's say we have f of 7t. What we're evaluating x at does not have to be a number. It could be some kind of a variable. It could even be some other kind of function of x. But let's say we're trying to do f of 7t. Well, that's just 3 times 7t minus 4. 3 times 7t is 21t. And you can't combine those terms because they're not like terms. So that's just a couple of examples to refresh your memory about what a function actually is. Let me try to get this a little bit more focused for you. There. Now, this next kind of function is called a piecewise function. You may or may not have seen piecewise functions before in another math class, like in Algebra 2. And this piecewise function is just a function that, like its name says, is made up of a bunch of pieces. It's a function whose definition changes. Like this would be the definition, 3x minus 4. Well, this definition is going to change. And it changes depending on the value of the independent variable, or x. So the definition is going to change. For example, here's a piecewise function, a very common one. Let's say f of x is equal to, and piecewise functions are always denoted by some kind of a bracket like this. And let's say it's equal to -x, and that is only when x is negative. And f of x is equal to +x, and that's when x is greater than or equal to 0. And what we're going to do with this function is we're going to just evaluate it at some different values of x. This is actually called the absolute value function. The absolute value function is really a piecewise function. Put that in parentheses. So let's say we have to evaluate a bunch of f of x values. Let's say we have to evaluate Let's say we're going to evaluate f of negative 3. Well, what we do is we look at the x value. The x value is a negative 3, and so we come up to this part of the function, because when x is less than 0, we have to evaluate this at negative x. So f of negative 3 is actually negative, and the x value, which is negative 3, which is equal to positive 3. And similarly, if you have to evaluate something like f of negative 60, well, negative 60 is less than 0, so you're going to call that a negative 60, which is equal to 60. Let's say we have to do f of 0. Well, 0 falls into this part of the domain. This x value is greater than or equal to 0, so f of 0 is just equal to the x value, which is x, so f of 0 is 0. And let's say we'll do one more. Let's say we have to do f of 16.1. Well, 16.1 again is greater than or equal to 0, so the f of x value is just whatever this x value is, which is equal to 16.1. So that's a really simple but very common piecewise function. Let's say we have to graph a piecewise function. So let's say our example this time is f of x is equal to, we'll put brackets down, let's say f of x is equal to x plus 2, and that is for the values of x that are less than 1. And let's say f of x is equal to x minus 1 squared, and that is for all the values of x that are greater than or equal to 1. So we have two pieces of this piecewise function. Piecewise functions can be a lot of pieces. You could add another one or so, and you can just change the domain. But in this particular case, this piecewise function is only in two pieces. So the first thing you're going to do is graph the first part, or graph the first piece. So we'll just set up our little xy axis here, and the breaking point on this is at x equals 1, so I'll just put a little 1 value on the x-axis. And everything for x being less than 1, your graph is going to look like x plus 2. So the function x plus 2, if x is equal to 1, then 1 plus 2 is 3. So on the y-axis we would go up to 3, and because it's strictly x is strictly less than, it really isn't part of that graph, so we'll put an open circle on here. If this said less than or equal to 1, we would fill in this circle. And x plus 2 is just a linear function with the y-intercept of 2 and a slope of 1. So we're just going to continue to go down here. This is negative 1, and here's negative 2. So here we go. Here's the first piece. That should be a nice straight graph, even though mine isn't all that straight. And then the second part of this is when the x values are greater than or equal to 1, then we're going to be graphing this second part, which is x minus 1 squared. Well, if x is equal to 1, we have the y value equal to 0. So we're going to fill this circle in right here, because this is x is greater than or equal to 1, so we consider x equals 1 on this. And then a parabola is just up 1 over 1, up 2 over 4, so this would actually go up to 3 comma 4 would be a point on this graph. So here's this piecewise function. Sometimes piecewise functions connect, sometimes they don't. In this particular graph, this is called a discontinuous function because it doesn't connect. Let's try one with 3 pieces. Oh, my instruction should say graph first piece and then graph second piece. Here's another example. Let's say f of x is equal to, and we'll have 3 pieces on this function instead of just 2. Let's say f of x is equal to just plain old 3, and that is when x is less than negative 1. Let's say f of x is equal to x plus 1 quantity squared minus 2, a little bit more complicated, and that is when x is in between -1 and +1. And the last one is, let's say f of x is equal to x minus 4, and that is for all values of x that are greater than 1. So the domain is all real numbers. We've covered all the real numbers here, and the range is going to be a little bit different depending on what the values are. So let's graph this little piecewise function. Well, usually what we're going to do is we're going to split it up at the breaking points. The breaking points are these values of x where the graph actually splits. So here's a -1, it splits here, and here's a +1, and it splits here. So for all values of x that are less than -1, the y value is going to be equal to 3. And this is strictly less than, so we have an open circle here, and we're going to go to the left. The next part of this is when x is in between -1 and +1, our graph looks like a parabola. So let's evaluate this at -1. So this would be 0 minus 2, which is equal to -2. So -1 comma -2 would be a point on that graph. Now let's evaluate this at x equals 0. So this would be 1 minus 2, which is -1. And the next point on this is when x equals 1. So 1 plus 1 is 2 squared is 4. 4 minus 2 is 2. So 1 comma 2. So this next piece, and we would fill in the circle because it does include +1. So this next piece of the circle is a parabola. And then the last part of it is when x is greater than 1, we are going to evaluate it at x minus 4. So if x equals 1, 1 minus 4 is -3, so we're going to come down to -3, but we're going to put an open circle on that. And again, this is a linear function, and the slope is 1, so I'm just going to go up 1 over 1, up 1 over 1, up 1 over 1. So here's the third piece of this. So this is again a parabola, or I mean a linear function, and a quadratic function, or a parabola, and a constant function. All three of these are represented with that basic piecewise function. And the last thing I'm going to talk about today is classification of functions into even and odd functions. So I'm going to talk about even versus odd functions. Just a couple of vocabulary words that are kind of important. So a function is even. Some functions are even, some functions are not, are odd, and some functions are neither even nor odd. So a function is even if, number one, if you evaluate the function at the negative x value, it's going to be equal to the positive x value. And another way of saying this is an algebraic way of saying the graphical way of if the graph is symmetric with respect to the y-axis. Oh, I've got a couple of ifs here. I don't need that other if. The graph is symmetric with respect to the y-axis. The third thing, another way of saying the above, is that for every point xy, every point on the graph, there is another point negative x comma y on that same graph. For example, here's an even function. Let's just use a very simple absolute value function. This is just y equals the absolute value of x. So this is even because let's say here's 1, comma 1, and here's negative 1, comma 1. These are 2 points on the graph. 1, 1, negative 1, 1. 2, 2, negative 2, 2. They're all points on the absolute value graph. So if I do f of negative x, if I do f of negative 1, f of negative 1 is equal to 1. And so is f of positive 1 equal to 1. So whenever I replace the f of x value with its negative value, you'll get the same y value out of it. This graph is symmetric with the y-axis. That's just another way of saying it, because it's a reflection of itself across the y-axis. And for every point x comma y, like 1 comma 1, 2 comma 2, 3 comma 3, there's another point negative 1, 1, negative 2, 2, negative 3, 3 on that same graph. So that's an even function. Next one is odd. A function is odd if, first of all, when you do f of negative x like you did up here, it's not equal to f of x, it's equal to the negative f of x. And another way of saying this graphically is the graph is symmetric with respect to the origin. Instead of the y-axis with respect to the origin. And for every point xy on the graph, there's a point negative x, negative y on the same graph. For example, let's draw this little function here, very familiar function. This is called y equals x cubed. So y equals x cubed has a point 1 comma 1, and it has a point negative 1 comma negative 1. It has a point 2 comma 8. It has a point negative 2, negative 8. So those are just, and 0, 0 is also on the graph. So those are 1, 2, 3, 4, 5 different points on this graph. 1, 1, 2 cubed is 8, negative 1 cubed is negative 1, negative 2 cubed is negative 8, and of course 0, 0 is on this graph. Those are just 5 example points there. And so if we do f of negative x, let's say f of 1 is 1. Well, f of negative 1 is negative 1. F of 2 is 8. F of negative 2 is negative 8. So whenever we replace the x value with its negative, we come out with the y value, who is also negative. The second point, if you remember from geometry class, a function is symmetric with respect to the origin. How I do this is if you turn this graph upside down, if you like rotate it 180 degrees through the origin, the graph looks exactly the same upside down as it does right side up. That's just my quick test to see if it's symmetric with respect to the origin. And like I said before, for every point xy on the graph, like 1, 1, 2, 8, there's also the point negative x, negative y on that graph, and you can just see that with those few points. So that's odd. But most functions are neither even nor odd. We'll just put that note. Most functions are neither even nor odd. For example, if we do f of x is equal to x cubed plus 3, if you remember from Algebra 2 class, x cubed plus 3 is just taking this graph and shifting the whole thing up 3. If you shift this whole thing up 3, it's no longer symmetric with respect to the origin. None of these 3 things would apply with that function. Or if you have something like f of x is equal to the absolute value of x plus 4, that would be like taking this absolute value graph back here and shifting it left 4. I'll just put up 3 of the cubic parent function, which is this one, and this is left 4 of the absolute value of parent. So I've just introduced you to a couple more parent functions, the absolute value function here and the cubic function here. So if you shift this graph to the left 4, this whole v would shift to the left, and then it would no longer be symmetric with respect to the y-axis. It wouldn't be a reflection if you moved it over 4. So those are just some basic vocabulary words and a little bit about functions. Have a great night. See you tomorrow.